All right, let's look at the equations of lines. There are a couple equations we would like to look at, and the first one is parametric equations, and the other one is a symmetric equation. All right, so let's draw a picture first. Let's say you have a line space. This is in blue. All right, in order to specify or identify a line, you need to know at least a point and the direction vector. So let's call this guy, let's say R0, which has a component, let's say x0, comma, y0, comma, z0, right? And then there's a direction vector. So say here, you can go either direction, but here, direction vector. So let's call that v, which has a component, say a, comma, b, comma, c, right? So in order to express the location, any point on the line, so I'm gonna just put a general point. So let's say you have a point R. It's going to be just a general point, and which is going to have, say, coordinates of x, comma, y, comma, z. Right? Then we can see that we can think of R as starting out with R0. Then you add the scalar multiple of this vector to get to this point. So we can write an equation of R, which is equal to R0. So that's the point. Then you add the scalar multiple. So I'm going to use t. So times the direction vector v. Right. And where t is any real number. All right. And if you write this component-wise, it's going to be x, comma, y, comma, z is equal to, so any point on the line can be written as x0, comma, y0, comma, z0 plus t times direction vector a, comma, b, comma, c. Right? And if you split that into components, so this is really the same thing as, right, x is equal to, so just look at the first component, so it's x0 plus ta, or 8, I'm going to write it as at, and the y is equal to y0 plus bt, and z is equal to z0 plus ct. Right? And this equation is called the parametric equation. Right? Because t is a parameter. Right? And another way to express the right equation for the same line be in a symmetric equation. Right? So what we do is we actually solve each of these three equations for t. Right? So you can see that t, if you solve for t from the first equation, you can see that, let's see, subtract x0 from both sides, so you have x minus x0. Then you have to divide through by a to isolate t, right? And if you solve for t from the second equation, you end up getting this. T is going to be equal to, right, y minus y0. Right, then divide through by b. Right, if you solve for t from the third equation, you will get z minus z0. over c, right? So this equation right here is called the symmetric equation. All right. All right, so it's just a couple different ways to express the equation for the same line. And you will notice that maybe I should write a note here. Note. All right, you can see a problem with this symmetric equation when one of these denominator or some of these denominators are 0. So for example, say if c happens to be equal to 0, then, right, so we cannot put 0 on the denominator. So what you can do is, assuming that a and b are non-zero, so you would have to actually write a couple of equations. So you have x minus x0 over a is equal to y minus y0 over b, right? Right, c is equal to 0 means that here, if c is 0, z is constantly equal to z0. So we have to write the equation z equals z0, right? So when you have a 0 component in the direction vector, what you need to do is you just have to set the variable equal to the point given, the component of the point given, because it does not change. All right, that's it. So those are the two ways to express the equations of lines. All right, that's it. I hope that this was clear.